Welcome. So, today we will be doing our exercises with transfer learning. So, in the last lecture we had discussed about one of these aspects which is called as domain adaptation, and domain adaptation as it goes down is through an experiment I had through one of the results from one of our earlier publication papers, and through a lot of other aspects I had shown you that if you have a classifier of some sort. So, not necessarily only a deep neural network, but then you have a classifier which has been trained on one particular data set to do a particular task, and then can you use all of this in order to solve another related kind of a problem. So, one of those examples was what we did with retinal images, in which it was trained on one data set called as DRIVE, which was more of from healthy people and was from a different camera, a different hospital and everything. And then when we wanted to use the same model which was trained to do vessel segmentation on that particular data set on a different data set, and then you saw this problem that initially it was not giving out good results if directly deployed. And then what we had an idea was, can we use some examples, at least a minimum number of examples over there, in order to make this come down to a convergent point, and will that be better than trying to train a network from scratch, which is using only the data from that other data set on diabetic retinopathy, which is called as STARE. Okay. Now, standing on top of that, on those experiments, what I said is that for deep neural networks, we had done our experiments till now using some of our pre-trained models, but then we never used the weights over there. We were just importing the model architecture and then we tried to do it. So, we had done it on LeNet, we had done it on VGGNet, on GoogleNet, on ResNet, on DenseNet. And over there what we had done is just take down the architecture and train it now for our own data set. And for us, most of these experiments we were doing it on CIFAR data set, which is just a 10 class classification problem, and the images are pretty small at 32 cross 32 pixels and color images. So, the only common denominator which was binding all of them was that these were natural images, and GoogleNet kind of networks which were also done were for natural images. But then all of these networks were for a 1000 class classification problem on ImageNet, and here this was just a 10 class classification problem. And we took this 10 class example over there from the aspect that it is easier to train when you have lesser number of classes, you will be requiring lesser number of data. So, it was just a good toy example to get started with around. Now, today what I am going to discuss is, if we take a network which was already trained to solve the ImageNet problem to a great extent. So, say these GoogleNets and VGGNet, then DenseNet, ResNet, which made up its real soaring appearance in CVPR on virtue of winning the ImageNet challenge. So, can we use all of these pre-trained models, and would that give us a leverage? Now, definitely looking down at the aspect of what we had learned from the earlier class, if we have a trained model and then we just try to refine it out, it would be much easier to do. However, then there can be multiple ways of refining. So, one of the ways of refining may be where I update all the weights over there for the whole network, but that is a costly process. Now, the other way you can refine it, that you just update that final terminal layer. Anyways, you will have to change the architecture for the terminal layer, since you are now not doing a 1000 class classification problem, but just a 10 class classification problem. So, let's look into what happens over there, and today's experiment will have something where I do not use a pre-trained model, I just train everything from the start, versus if you use a pre-trained model and then either modify it partly or modify it end to end, and then what comes out. Okay. So, over here as it goes through, if you look into the codes over here, then you can see down that the first part is pretty simple and standard. That is the header which we have been using as of now for all of our experiments. We do not make any change over there. Next comes down our data. So, for the data we are using CIFAR 10, and now since this particular experiment deals with GoogleNet, and what we had seen is that GoogleNet by its core virtue over there is something which was requiring 299 cross 299 pixel image, not 224 cross 224 sized images over there. And for that reason, we had to scale and transform these images over there. And once you have the scaled version of images at 3 cross 299 cross 299 available, then you can work it out. And we also choose down a smaller batch size. In fact, here we have even a lesser batch size of 8 for the fact that we would be training actually 3 networks, and that is going to consume a lot of memory on our side as well. Okay. So, let us get down to this one. So, there is the train loader and the test loader, the train set and the test set, which are completely created out, and we are just going to make use of that. Now, so, since we have the data and file already there, it's confirmed and it works it out. So, the CIFAR data set which we have is of 50,000 examples on the train set and 10,000 examples on the test set, and then here we start with defining our network. Now, if you look into the first network, this is the one which is similar to the definition which we had created in the earlier case example, which was just pull it down from our Torch Vision library of models, and this is Inception V3 which we were using. Now, I create the next network which is the same as over here, except for the fact that I use this pre-trained equal to true argument over there, and what this does is it does not just pull in the architecture from the web archive source, but it also pulls in the weights over there. So, all the pre-trained weights will now get imported, and I am going to make use of this pre-trained model. So, this is something which is already trained for solving the ImageNet problem, and now we are going to look down whether it is able to solve the CIFAR 10 classification problem as well. Okay. So, then we define another one which is called as net3, and net3 also has the same kind of a mechanism over there. The only change comes down is that in net2, so this is what we have commented over here. So, net2 is the network which we are going to do end to end fine tuning, which is you replace the last layer of 10,000 nodes of 1000 nodes and then replace it with just 10 nodes over there. When you are training, you are going to do the whole error backpropagation over the whole network. In the other one, what we are going to do is we are just going to update the last layer weights. We are not going to update the complete network over there. So, this is the change which we will look down, and we will look into. So, one aspect is that when you are just updating the last layer weights over there, so your total compute complexity is really coming down because you do not have to update the whole network at a go. On the other side, we really need to look at that at this reduced compute complexity which we are offering. So, that is a gain for us definitely in terms of the compute potential for the network. The loss is in terms of decrease in accuracy. So, is accuracy significantly decreasing because of this reason, or can it really keep on still working out? So, this is the actual motivation of the whole work over there. So, we just print down net1 architecture because as such it does not print weights if we are just printing down the network over there. So, net2 and net3 will have the same architecture which looks out. So, that is the straightforward thing which we had for Inception, and we just have that. Now, what we do is, so this one was looking into the total number of parameters over there and then to count it out. So, this was another part which we had done earlier this week, which was to look into the theory of actually finding out the total number of computational parameters. Now, if you go down through this part, you would be able to find out the total compute parameters as we had done in the earlier experiment on GoogleNet, and that was something around 27 million parameters over there. Now, once that gets over, the next part is to do this architecture modification. So, as you remember that in all of the cases what we were doing is that the last layer over there was getting replaced from a 2048 to 1000 neuron connection. Instead of that, we are just going to replace it with 2048 to 10 neuron connection, as well as the same kind of a thing happens for the auxiliary layer as well, because in each of these things you again have an auxiliary layer. So, the auxiliary layer also gets replaced from a 768 neuron to 1000 neuron connection. Instead of that, we are going to put down 768 to 10 neuron connections over there. So, these are the two modifications which we do for all the networks. And again, recalling back from the GoogleNet lecture over there. So, the particular model which we are using in Torch in PyTorch over here is the one which just has only one auxiliary classification arm. It does not have two auxiliary classifications, and for that reason we just stick down to changing only one of these arms over there, because there is not the other one in any way. Okay. So, now what we do is we just copy down our weights, the initial weights over there. Now, keep in mind one thing, that for your net 1, this is which is randomly pre-trained, this is randomly initialized, this is not at all pre-trained. Net 2 and net 3 are the pre-trained models. So, net 2 and net 3's initial state weights are the same in both the cases, they do not mix up in any of them, and net 1's weight is very different from net 2 and net 3. Okay. Now, we get into the part on GPU availability. Now, it is if it is available, then there is a typecast operator, and we are done in the previous lectures on what happens during typecasting and how there is a DMA transfer and the whole model as well as the weights, and the data itself gets transferred over there. So, this part is also quite clear with you guys on what we were doing with the typecasting and what was the compute equivalent on the computer hardware side of it, what was it initiating on a hardware aspect as well. Now, from there coming down to the loss criteria, and they are pretty simple. So, since we are solving the classification problem, so it is the negative log likelihood loss which we are taking down, and then the optimizer is Adam for all of them, and the learning rate over there is also kept constant. Okay. Now, having said that, there is one critical aspect which we need to look into it. So, for network 1 and network 2 is where we are going to do end to end. So, network 1 is which was randomly initialized, and then you had trained it from the final node to the initial layers over there. Network 2 is which is already pre-initialized with the weights from solving the ImageNet problem, and we are still going to update the total weights of the all the layers from the last layer till the first layer. Network 3 is where we are going to freeze in the weights of the layers from the first till the terminal one. So, only the last layer which is for connecting down 2048 neurons to 10 neurons, that is the one which is getting updated, everything else does not get updated. Now, as a result, when I am not updating anything else over there, so I do not even need the auxiliary losses, because there is no backpropagation happening for all of them. So, they are the ones which are going to remain preserved. Now, that is the change which we have in the code. So, in the code, if you look down into the parameters, what we do for network 3 is we just use this fully connected parameters over there of the FC layer. So, this was this FC layer which we had changed over there for each of them. Now, we are going to just use the parameters over here in order to optimize, and what that would mean is that these are the only set of parameters on which the update rules are going to run. On the other parameters, the update rules are not going to run, and you will end up updating only the last layer for this network. Okay. So, now once that goes down, we train this model just for 5 iterations, because some part of it is already trained. So, it is easier to show it to you. The other downside is that it takes really long. Say GoogleNet per epoch was taking down like about 8 to 9 minutes of it to train down, and now since we have 3 networks to train down in one single shot, so over there it takes about 24 minutes or roughly half an hour of time to train it. So, going it down for more epochs is going to take more amount of time. So, for us we have just done it for 5 epochs. In fact, within 5 epochs it does come down to the saturation point what we wanted to show on the performance characteristics. Okay. Now, there goes down the losses and accuracy tensors which we needed for each of the 3 models, and then we start for each of the model over there. Now, within an epoch, I am going to load down one batch of data. Now, for that batch of data, I just see if it's if there is a GPU available, then we just do a CUDA typecasting, which is to get the DMA transfer of the batch of data onto my GPU RAM, so that it can work over there. And then my first part is do a feed forward over it, collect down the outputs from the auxiliary arm as well as from the actual terminal output over there, and then do a final classification accuracy compute over there. Now, once this accuracy is computed over there, now what we need to do is you will come down to your optimizers and then actually create down zero down all the gradients intermediate over there. Then do a criterion based loss function compute for the auxiliary node as well as for the main terminal node over there, and then find out what is your total loss for the model. And this is what you keep on storing, as well as within your optimizer you are going to make use of all of this and do an optimizer dot step which just runs the update rule. Now, since in your first 2 networks, network 1 and network 2, net 1 and net 2, you had collected down all the parameters to be used within Adam. So, all the parameters are getting updated. In net 3, we had just used the last fully connected layer, and so the updates which happen down are only in the last fully connected layer over there, and nothing else gets updated or modified in any way. Okay. Now, once that is done, we have our losses, accuracies and everything taken down and averaged out over it, and then within each epoch I am also calculating out my validation scores. So, this is on the test data set which is left over there. So, at the end of update of one of these epochs, how much is the change which happens during the test performance for the model. So, this is what I compute out, and it pretty much goes on in the same way. The only difference over here is that instead of using one network, we have 3 networks which we are using, and then I decided to plot all of them. So, let us go down and look into the models and how they are training, and then come down to it. Okay. So, within each iteration there are 3 models which are training down over there. So, if you look down at the training loss, so the first model which was a randomly initialized model, it starts with a much higher loss, whereas the second model where you had done a you had just modified only the terminal node over there, that is the one which has a lower loss, while the other one is where you had modified the terminal layer, but not updated all the weights, you had just modified only the terminal layer weights. So, in net 2 is where you do an end to end update, in net 3 is where you do only the terminal layer update. So, it trains out definitely much faster, but then the loss is not so low. So, the loss is relatively high over there. Now, if we keep on going through the network, what you would find out is that at the end of 5 epochs over there. So, for model 1 the loss is somewhere around 0.06, for model 2 on net 2 is where you had updated the whole network end to end for CFAR problem is around 0.1, and for the last one where you were just updating the final layers is where the loss is a bit higher. Now, if you look even at accuracies, what you see is that the first model where you had started with a random initialization, a random guess over the weights, and then updated all the weights together, that has a higher accuracy on the test data set as compared to the other model where you were updating only the last terminal nodes. So, this definitely means that one point which I was emphasizing on the lectures on domain adaptation and transfer learning was that you need to really update all the weights and features and everything over there, not just the classifier layer over there. So, it may be that your features over there are not quite specific to the actual problem which you are dealing with, and they might also need to get an update. So, this is a clear example where you can see this discrimination coming down, where in the first case when you are updating all the weights over there, so you see an accuracy come down to at 81%, whereas in the last case where you were updating only the last layer weights over there, so the accuracy does not go up that high, it just stays at 74%. Okay. So, we look into this part over there. So, this is the auxiliary loss. Now, look into one thing, in model 3 is where we were updating only the final layer. So, we were not collecting the auxiliary arm parameters and updating that, though we were collecting the losses and there was this arm kept over there. So, this remains fixed, this does not change in any way. And for the other two models, you would see that the auxiliary loss also keeps on decreasing substantially. Now, model 1 is where it was a random guess, so it starts with a much higher one and then keeps on going down. Now, in the next case is where you see for the first network 1, where I was training it from scratch and doing it. So, this is how my train and test losses are decreasing, and this is how my accuracies are going down. So, you see crossover point at about the 5th epoch itself is when my train accuracy is increasing, but my test accuracy is now either saturating or trying to decrease out. So, this is the first crossover point which comes down over there. Now, this is for my second model where I was doing an end to end update based on the training over there. Now, definitely it comes down much faster towards a convergence as compared to the earlier model where it was not initialized based on some clever guess, but it was a random initialized one. You see that the crossover also takes place much earlier. So, this is already at the at this point. So, which is almost like this is the first epoch, second epoch. So, this is my third epoch. So, in between the second and the third epoch is where the crossover is already taking place over there. So, maybe just after 2 epochs you can just stop it, or maximum you can go up to 3 epochs and then you see that the whole network is updated. So, this is much faster. So, if you look into the earlier case, you do not get this much of an accuracy of say 94% in the in single shot over there. So, if we look into the first case, which is this model, so at the end of third epoch, which is somewhere over here, I have an accuracy of 75%, but then if I start down with my weights which are taken down from the ImageNet problem, and then at the end of third epoch I am already at 94%, which is really good, and that is the advantage which you get done with the transfer learning of using a model which was trained on a similar or on a related kind of a data for a related kind of a problem, and then just modify it. So, you have a much higher accuracy coming down with just lesser number of epochs of training. And then if you look into the last one where I was looking into just modifying the final nodes over there. Now, that will not always be helpful because you still see that you are limited at the below 75% accuracy in either of these cases, and the so the train accuracy is also lower, though the test accuracy or the generalizability is much better, but then on that your test accuracy is still limited below 75%. So, this is another critical fact which you need to keep in mind, that always updating just the final terminal nodes might not always be the best possible solution to go around with. So, once we have that, the next idea was to so this is where it's just the same kind of plot, but taken down into the same thing together. So, this is my train loss and my test losses. I also have my test accuracy plotted down over there for all 3 of them. So, if you look into it, your model 2, which was a pre-initialized model, and then just being updated over there. So, your test accuracy is really keep on increasing, and it is definitely a few folds higher than your other models over there, model 1 and model 2, model 1 and model 3. Model 1 which was just randomly initialized and trained, model 3 is where only the final nodes were getting updated. So, now let us look into the weights over there. So, this is for my model 1 where I had my random initialization. So, this was the weights for the first convolutional layer. So, you have 3 cross 3 kernels over there and 1, 2, 3, 4, 5, 6, 7, 8 and 8. So, that was sorry 4 and 1, 2, 3, 4, 1, 2, 3, 4. So, there were 32. So, you have 32 channels over there and 3 cross 3 convolutional kernels over there which you had for the first layer. Now, what you see is these were the random initializations which had been done. This was the update after after at the end of 5 epochs over there, and these were the change of the weights which you see. Now, for your second layer over there, this is what you observe over there. Now, in the second layer definitely because the input was 32 channels over there. So, we just display for one of the kernels all the channels coming down over there. Now, if you look into the second model where you had taken a pre-trained model. So, these were the weights at the start of the training process and these were the weights at the end of the training process over there, and these were the difference of the weights which were coming down. Now, if you look into the second convolutional layer over there. So, you see these were the initial final states as well as the difference coming down. Now, here comes the interesting part which was the model 3, in which what I was doing is updating only the final nodes and I was not updating anything intermediate. So, these were my starting states, and since I was not updating anything on the previous layers over there. So, this becomes my ending state and my start state and end state is the same, and for that reason you see that your weight difference matrix over there is completely 0. So, there is no update which is happening over there. Similarly, is the case for the second convolution layer for the network 3 as well. So, this is what we have as a clever and clear exercise for doing your transfer learning on any kind of a deep network. So, this was one example just using GoogleNet, in which you have the aspect of an auxiliary arm as well, and then how do you do this, either a full end to end training or you are just concerned with the last final edge of final classification terminal nodes over there. So, now one thing which is clear from these graphs is that definitely it is always advantageous to take down a model which is pre-trained, and for you it is going to consume lesser amount of your CPU time. Yes, it does take more amount of time to download the model, because the model is not just the architecture definition, it also has the weights over there. So, that is the additional bytes which you will be downloading over there. On the other side of it, your CPU time which is going to get consumed is lesser. Now, the next fact is will you be updating only the terminal layer? Now, this is case to case dependent, we cannot directly comment over here, but typical practice is that only updating the terminal layer might not be a very good idea, because your features might not be optimum for your particular data set which you are looking. So, if you look into image data sets from ImageNet, which are 224 cross 224 sized over there, the granularity and resolution is much higher, whereas for CIFAR it is a smaller sized image, they were just thumbnails of 32 cross 32. So, once you scale it up, in fact there is a lot of blurring which comes down around over there. Now, the features associated with trying to identify an object which is blurred versus the features associated with trying to identify an object where the image is very crisp and of a high resolution are going to be very different, and for that reason what you would find out is that this particular model does not work out good if you are just updating the final layer. Whereas, if you go down for newer kind of problems where say ActivityNet is a new challenge which comes up, a lot of people have a good way of just trying to take a pre-trained GoogleNet where this GoogleNet was trained on for the ImageNet problem, and then you update only the final layers, you do not update everything, because on ActivityNet also your videos are almost of the same size of 224 cross 224, and they are natural looking images, they are of high resolution. There is this mismatch of early level or low level feature descriptors is not there. So, that is what we have for the transfer learning as of now. We have the next lecture where we are going to cover down transfer learning with residual networks as well. So, what happens within residual connections, and what is an advantage which you gain, and if there is some disadvantage as well. So, we will be doing the same thing and then repeating it once over again to check down what goes down over there as well. So, with that we come to an end to today's one, and thank you.